Hi, welcome to Java DevOps and SRE series. Today we are discussing Java interview questions real-time scenario part 3. Here is our first question. How does JVM memory structure work? When a Java program runs, the JVM divides memory into three main parts: heap, stack, metaspace. There are few other like PC register and native stack, but these three are the most important. Heap memory. Heap memory is where all objects are stored. It contains objects created using new instance variable arrays. It is divided into young generation, hidden and survivor spaces, old generation, also called tenured. Here is how objects move. Object is created in hidden. If it survives garbage collection, it moves to survivor. If it lives long enough, it moves to old generation. Garbage collection works in two main ways. Minor GC happens in young generation. It is fast and frequent. Major or full GC happens in old generation. It is slower and more expensive. Here is an example. The object is stored in heap. The reference variable S is stored in stack. The common problems are memory leak, objects not released, GC pauses, which causes latency spikes. Stack memory. Each thread has its own stack. It stores method calls, local variables, reference to objects. Stack. Each method calls create a stack frame. It contains local variables, operand stack, method related data. For example, here X and S reference are in stack. The actual high object is in heap. The key properties are stack follows LIFO, last in first out. It is very fast and automatically cleaned when method finish. Stack overflow error happens when there is deep recursion or infinite method calls. Metaspace. Metaspace replaced PermGen in Java 8. It stores class definitions, method metadata, static variables, runtime constant pool. The key differences are Metaspace is stored in native memory, not in heap. It can grow dynamically. Metaspace out of memory error happens when too many classes are loaded. For example, dynamic class generation or class loader leaks. How everything works together. Here is an example. Class is loaded into Metaspace. Main method creates a stack frame. Reference P is stored in stack. Person object is created in heap. Advanced. Escape analysis. JVM may allocate object in stack instead of heap. TLAB. Each thread gets a fast allocation space in heap. GC algorithms. G1 GC is most common. ZGC are low latency collectors. The real production issues are memory leak, which object stays in heap forever. GC pause. Full GC stops the application. Class loader leak. Metaspace creep keep growing. JVM memory is divided into heap, stack, and metaspace. Heap stores objects and is managed by garbage collection. Stack is thread specific and stores method execution data. Metaspace stores class metadata in native memory. Most real world issues come from memory leaks, GC pauses, stack overflow, or metaspace exhaustion. Our next question is, how do you make a class thread safe? A class is thread safe if multiple threads can access it safely and behavior remains correct and predictable. Real time scenario is payment wallet service. Imagine a wallet with 1000 balance. Thread A detects 300, thread B detects 500. Without thread safety, both threads may read 1000 at the same time. Final result become wrong. This is called a race condition. Here is an synchronization approach. Using synchronized keyword, only one thread can access the method at a time. It guarantees safe execution, but problem is poor scalability. Thread get blocked, performance becomes slow. Another approach is reintrant lock, gives more control compared to synchronized. It supports try lock, timeouts, fairness policies. Another approach is atomic variables, using atomic integer lock-free operations. The pros are high performance but only works for simple operation. Another approach is immutability. Create object that never change. Every operation returns a new object. No synchronization needed, naturally thread safe, but creates more objects. Another approach is concurrent collection. Used when multiple threads modify shared data. Check then act problem. This is not thread safe. The fix is use the synchronized method or atomic compare and set. The real systems we don't rely only on in-memory logs. We use database transactions, optimistic locking, distributed logs like Redis. For example, SQL update ensures atomic operation. Balance is updated only if condition is satisfied. To make a class thread safe, control shared state using synchronization, logs, atomic variables, or immutability. In real systems like valid service, avoid race condition using database level atomic operations or optimistic locking. The pro tip is that thread safety is not just about adding logs, it is about choosing the right strategy based on performance, contention, and system design. Thanks for watching.